So what we're going to do today is we're going to talk about velocity and acceleration, and we're going to talk about graphs. Okay. So the next day or so is going to be sort of, lecture focused, and then we're going to do some physical things. We're going to talk about this stuff physically, but I want to talk about the math behind this, and then let's talk about the tangible parts, and then we'll sort of connect them. Okay. So we've got there's a couple things we're going to look at, okay? We're going to look at motion in a few different ways. All right, we're going to look at position or displacement. I'm going to use P for a moment. Now, I've talked about distance and displacement, but I'm going to use P for position. The reason I'm going to do that is because it's going to be where you are in time, okay, versus time, okay? We're also going to look at that relation to velocity in time. We're going to talk about what that means in a minute. But when I look at graphs, are you guys familiar with graphs? You guys done a bunch of graphing at some point?
Yeah.
Okay. So if I put like hash marks, right? You could plot. If I said, okay, if these are all meters, right, and these are all seconds, let's say each hash mark was, a 1 second or 1 meter, okay? So let's say, and this is like a 0, 0, this is the beginning, your origin. So I could say, look, at 0 time, at the beginning of time, let's say you're at your start point, you're at 0, okay? At 1 second, let's say you're at 2 meters. So I can see 1, 2, bump, 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 right? Let's say at 2 seconds, that's 1 second, that's 2 seconds. At 2 seconds, let's say you're at 4 meters. That's 2 meters, 4 meters. And at 3 seconds, okay, we're at 6 meters. Okay? Do you guys see that? So all I'm doing is I'm plotting a location. So as time moves on, I'm changing my position. That means that let's say I have okay, so he's sort of walking along. Actually, it's a horrible. All right, he's sort of walking along, okay? That means that this individual, let's say at here we've got 0 meters, okay, and we're going to have 2 meters, 4 meters, 6 meters, and so on, okay? That means that at time 0, that's what this looks like. So this is a snapshot at time 0, okay? I'm going to erase this here for a second. I'm going to move this over here so we kind of see what we're doing. Shrink this down a little bit. Okay, oops. So he's over here, okay? So that's time equals 0. So this is time equals 0, okay? So, and this seems a little rudimentary, but I want to be very clear about this. So at time equals, 1 second, that's 0 seconds. This is 1 second. All right. My guy, where's my guy? Where's my guy at 1 second? 2 meters. So he's over here at 2 meters. Does that make sense? Okay. Notice he's not here anymore. He's here. This is just noting where he is at time. Okay, we're going to bring him down again. And now we're going to say this is at 3 seconds. Oops. At 3 seconds. Okay, where's my guy at 3 seconds?
6.
At 6, right? 2, 4, 6, right? 2. Oh, it was 2. Oh, I missed 2 seconds. Sorry, let me do 2 seconds. My bad. I missed 2 seconds. This is at 2 seconds. He's at 4 meters, right? And then at 3 seconds, where is he at? 6, okay? He's over here, okay? So we're seeing him move along, and this is just his position versus time. This tells us nothing right now, unless we do some math, just his position over time. So I could tell you guys, look, or I could ask you, look, plot his position. If I say, okay, he's moved to here, and he's moved to there at this time, and he moves to here at this time, you need to be able to plot where he is. Now, that being said, maybe he doesn't always have to start at 0, 0, okay? Maybe at 1 second, at 0 seconds, he's actually starting here at 2 meters, okay? So just because I started here, and what I'm trying to do is I'm trying to hit some of the points that I saw last year where I got some confusion. So there's an assumption, because this time at 0 time, he starts at 0 meters, doesn't mean he always has to start that way. Okay, he could actually start where this is actually 0 seconds. Okay, if this was 0 seconds, following the and this was 1 second, and this was 2 seconds. Following the pattern, what would time equal? What would time be here? If this is 0 seconds, he's at 2 meters. 1 second, he's at 4 meters. 2 seconds, he's at 6 meters. When he's at 0 meters, what's my time? Not -2, it's -1 second. Does that make sense? And at -2 seconds, where's he going to be? Let's look at that. Okay, so this is where, this is good we're doing this, okay? Let's say that's -1, right? Okay? At at time equals -2 seconds, where is he? What's his position? Look at the pattern. Look at the pattern. Where is his next position going to be?
0.
At -2 seconds, not 0. He's at -1 second, he's at 0. Okay? Right. Okay, he's going to be at -2. You guys see this? No, let's talk about why. Okay, so he's going to be at -2 meters. You guys see? I know you were originally saying -1, but do you see why it's -2? Okay, look, every second, so 0 seconds, he's at 2 meters. 1 second, he's at 4 meters. He's got a difference of 2 meters, right? So the distance is, and the next second, he goes from 4 to 6. So it's 2 meters. 2 meters, 2 meters, 2 meters. So if I go backwards in time, if I follow that same pattern, it should be at -2 meters. Do you guys see it? Does everyone see it? This is important, okay? Because what we're getting here, Gabe, wake up. Gabriel, you can wake up, or you can go. You can snooze in Mr. Gunnan's office. What would you like to do? Okay, take some notes out. This is important. All right. It's important because we're noting we're doing some things. What are the 2 things we're changing here? What are the 2 things that are changing that we're watching change? His distance and his time. Okay. So if I look at the delta time, each piece here that I've got now, I've picked 1 second, 2 seconds, 3 seconds. Could I have picked any other time? Sure. But for right now, I've picked this second. So for every delta, so what's the difference in time between this point and this point? What's the difference between here and here? What about from here to here? Everyone? Okay. So delta time is 1 second. For every 1 second, I have a delta distance equaling what? 2 meters. So every increase of positive 1 second, I increase a positive what? 2 meters. Okay? So this is really important because does anyone know what this is called mathematically? Anyone remember this? Begins with an S. Let's look at this. Here we're plotting it, right? Where's the next point going to be? The next point's going to be
Slope.
it's slope, right? So 1 second, we're going to be -2. Here's the point. So I can actually draw a line, okay, a graph that's roughly getting to the points like that. Okay, now my points are just off, but they should fall on that line. Okay. So this delta distance over delta time, is a slope. It's a slope of the curve. It's my delta distance and my delta time. Okay? Does everyone see this? This is critically important. Why is this slope important? What does this do for me? If this line is straight, what does the slope do for me?
Call out any particular time and you can say how far it would be.
Nicely said. Okay? This slope allows me, and I'm going to use a P word, that allows me to predict where I'm going to be at any point in time. Or it allows me to predict if I'm at a specific position, what is the time that has elapsed. Does that make sense? Going forward or backward. Here's the best thing. At time equals 1.5 seconds, where is he? At what? No, at 1.5 seconds, he's at 1 second he's 4, at 2 seconds he's 6. At 1.5 seconds, where is he? 5 meters. Does everyone see that? He's somewhere in the middle, halfway between. Now, I know he's halfway between. How do I know he's halfway between? And because my curve is constant, my slope is constant. Okay? If for every 1 second I go 2 meters, 1.5, okay, times 2 is what? 3. Okay, oops, I'm sorry, hold on. 2, 4. Oh, okay, I'm sorry, because I went every 2 meters, 1 second, 2 meters. Oh, because I started from, it would be 3, but because I started at -1, I started at 0 is 2 seconds, that's the reason why. 3 plus 2 is 5, right? And I started at 2. So really, this scenario, my slope is where? Where's my slope? It starts at 2 and is at the same rise. Now we're here, right? So if I look at 1.5 seconds, now I'm at here. Do you guys see that? So, and I made a jump, and I apologize because I put a couple things in a row here. But at 1.5, he's at 5 seconds because 1.5 times 2 is what? 3. But he started at time 0. He started at 2 seconds. So 3 plus 2 would be 5. Did that confuse you guys? You with me? Okay. So the original setup was where we had the position where we intercepted the y-axis, the position axis at 0. But because I shifted my time, this is my y-intercept right here. And that means is at 2 meters at time 0. So I shifted him. Here's the same slope. Does that make sense? We'll do another one in a second here, but I want to make sure we're sort of getting this. Does that make sense? Okay. Let me go and let's do this. Let's start this again here. Actually, let me come over here. Let me grab this guy. Okay. So we're going to do this again. We're going to say, okay, time equals 0 seconds. Okay. And let's do all right. We're going to say See, my hashes aren't exactly the same, and that's problematic. All right, this is going to be time and position, or I'll even call it distance for the moment. But remember distance being the position that I'm at. Okay, and we'll call this 0, 0. All right. At time equals 0, this note shows that my guy is starting right here. Okay? Let's say he had a slope of 3. What does that mean? Let's think about that. So if my slope equals 3, what does that mean?
For every second he moves 3 meters.
Okay. So this means that my delta distance over my delta time, that ratio, is 3. And let's say it's 3 meters per second. That means that for every 1 second, he goes 3 meters. Okay? So that means at 1 second, where is he? 3. So here's 1 second. 1, 2, 3 meters. There he is. Okay? And actually, what I think I'll do is I'll do it. I'm gonna do it so every mark is 3 meters. Okay. Now notice I can make the marks however I want. It's up to me. I'm gonna make that mark 3 meters. So the first one is going to be here. All right. At 5 seconds, where is he?
15 meters.
Everybody, at 5 seconds, where is he? Okay, so 1, 2, 3, 4, 5. So it's 3, 6, 12, 15.
You missed 9.
Oh, thank you. Thank you. Thank you for being awake, Gabe. 3, 6, 9, 12, 15. Okay, so now he's at 3 seconds. And he's at 15 meters. Okay, so this means that, oops, hold on.
You asked where he'd be at 5 seconds.
At 3 seconds, 5 seconds would be 15. Oh, I'm sorry, I did that again. My bad. Thank you. We're at 5 seconds. And there we go. All right. Like that. All right. And so that means that I can predict, again, where he's going to be at any point in time. Right? So at 3 seconds, where is he going to be? 9. Okay. Boom. 9. Right? Okay. Where is he going to be at? Where, if he was traveling, we caught him. We decide let's say he's traveling forever. Okay. But we caught him today. And today we're going to say, oh, snap. We're going to say this is 0. This is our initial time. Where he is, it's 0. That's a 0 position. But if he was traveling, that meant before we got to him, while we were hanging out, he was still traveling, right? So he had come from somewhere. Okay? So if that's the case, then the question is, at time, I could ask the question, at time is negative 3 seconds, where is he? At negative 3 seconds earlier, where was he? Negative 9 meters, right? Okay, good. I'm glad we've got this. This is good. All right, so here's 1, 2, 3. Okay. All right, so we've got 3 we got 3. Oops, excuse me, I did this wrong. 1, 2, 3, and doom, 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 doom. There we are. Boom. Okay, so at negative 9 meters, and this is negative 3 seconds. There he is. So we can predict both forward and backwards. Okay. We talk about this slope. Okay, and this slope being the change of his distance over change of time, and that is our velocity. Okay? And we look at this and we say, okay, here's a delta distance, and here's a delta time. Okay? Now, I chose in this case, the way I drew it, what's my delta distance in this case? What's my delta distance? But what is it? What's the actual number? How do I determine the delta distance from this point to this point? Okay, I'm subtracting 9 from 15. So this is an important note, because as we go forward, I want to make sure we're clear about this. Delta anything is equal to the final minus the initial. Okay? So in this case, for this specific thing, the delta distance is equal to, what's my final distance when I'm looking at this slope right here? 15 what? And what's my initial distance on this little slope part? Everyone see that? 9. So 15 meters minus 9 meters. That's my final minus my initial when I'm looking at that particular window of time. Does that make sense? I could start at 0 and I can end anywhere else. We're going to talk about that. But for right now, this one piece, I'm looking at 15 meters and 9 meters. Those 2 points. Okay? My delta time. What's my final time? At 15 meters, what's my time? 5 seconds. What's my initial time? 3 seconds. So if I say 15 minus 9, what is that? 6 meters over what's 5 minus 3? 2 seconds. And when I reduce that, what do I get? 3 meters per second, which is the same slope or velocity I started with. Do you guys see that? And let's do another version, okay? Let's say, I'm going to get rid of this for a second. Let's say I said, well, delta distance now. Let's say I looked at this point versus my initial point. So the end point versus my time 0, right? So that means delta distance over delta time. What's the delta distance for this triangle here? What's my delta distance for this triangle from this point to this point? From here to here. So 15 meters is my final. What's my initial? 0 meters, right? What's my final time? 5 seconds minus what's my initial time? So that's 15 meters per 5 seconds. And when I reduce that down, I get 3 meters per second again. So this is an important thing that I think got lost last semester because I made some assumptions. And so I want to take some time and go through this. Even if it's redundant and slow, I apologize and I gave you feel you've got this, but I want to make sure that everyone gets this. This is really important because what we have here is we have a prediction. And as long as this line has the same slope, okay, the slope being the rise over the run, in this case, delta distance over delta time. This slope is the same, no matter if I look at this guy, this small triangle, this big triangle, or this even smaller triangle. What do they all have in common? They have the same what? Slope. Okay? Which means that we call this, anything with a constant slope, constant distance, I'm going to say delta distance over delta time slope, means we have a constant velocity. What's my velocity? What's my velocity? 3 meters per second. No matter where I check it out, I'm going 3 meters a second. Okay? I'm going constantly 3 meters a second, no matter where I am in time. If this has a constant slope. Okay? Does this make sense? Okay. What does this mean? What does this mean? If my curve looked like this, don't talk about velocity yet. Just say, what does it mean? Think about what this means. I'm not moving. Why do you think I'm not moving? As time moves along, my position is not changing. So I'm standing still and the clock is ticking. My position, am I traveling at a constant velocity? Yes. What is my velocity? Zero. Beautiful. That's what I want to make sure we're clear on, okay? We're at a constant velocity, though my velocity is zero. I'm standing still. Is that clear? Okay. All right. Next piece I'm going to hit here. Let's say I have a slope like this. Let's just say, for argument, we're saying distance, distance and time. Let's assume that my slope, my delta distance over my delta time, delta distance over delta time, that's going to equal my velocity. And it's a vector, because it's got a direction, it's forward, right? Okay. Let's assume that I've got that velocity. At some velocity, let's assume it's 5 meters per second. Okay? So let's say at time 10 seconds, what's my distance? At 10 seconds, what's my distance? How far have I traveled? How much? All right, well, let's do the math for a minute. Let's look at the math part, okay? So if my delta distance over my delta time is 5 meters per every second, okay? And I know my time, right? And I want to understand my distance. If I had delta d over delta t, and I wanted to get rid of my time and keep my distance, what would I have to multiply this ratio by? How do I get rid of delta? How do I get rid of delta t to get to leave delta d? Not the top and bottom.
Or the top of the inverse.
I multiply it by delta t over 1, don't I?
Yeah.
Because now if I do delta t over 1, my time cancels. I'm left with delta distance. Does that make sense? So up here, if I say 5 meters, okay, times 10 seconds over 1, my seconds cancel. This is unit analysis, and I want you guys to do it this way. I'm going to equal 5 times 10, which is 50. What's my unit that I'm left over with? Meters. Over what number do I have in the denominator? 1. So it's really 50 meters. So after 10 seconds, I have gone 50 meters. Does that make sense? So the change in velocity, I'm sorry, take that back. My change in distance is equal to my velocity times my delta t. Well, let's look at that for a second. We said that delta distance over delta time equals velocity, right? And if I want to get delta distance alone, I'd multiply both sides by delta t, and those cancel, and I'm left with this. Does everyone see that? So my delta distance is equal to my velocity times my delta time. And this is, and I talk about, look, I very clearly do not say this. I very clearly do not say d equals v times t. You will see that in your book. Take that page out, rip it, burn it up, throw it away, have a ritual over it. It's horrible. It's absolutely horrible. This is incorrect. Why is this incorrect? Because it makes a big assumption. What's the assumption that this initial equation says? Does anyone have any idea what the that's a bit, but both of them are, my slope is constant, still here, right? But what it assumes is that my initial distance is 0, and my initial time is 0. And that is not always the case, okay? So be very careful that you don't say d equals v times t, because that is a misnomer. it makes a huge assumption. And that assumption, though intuitive, right? Usually we start at 0 and we start at time 0 and start at a position. When we start to do problems, we start to do some math, this will cause a huge mental block for you guys. So don't do this. Get rid of that. If you ever see it, look away. Look away. Hide your eyes. Okay? All right? Should be delta distance equals velocity times delta time. All right. Does everyone understand this? And so I can solve for I can solve for my delta distance. I can also solve for delta time, right? So if I had delta distance over delta time equals my velocity, how do I get my delta time? What's my delta time equal to? Let's do the math. How do I get delta t by itself? So I got to multiply both sides by delta t. Okay, so that cancels that. But now I've got this guy, right? That gives me here, right? How do I get delta t by itself? Then I divide each side, delta d, by velocity equals delta t. And I divide that. If I divide this by velocity and this by velocity, then these cancel, and I'm here. So you can work that. You can work that position, that thing anytime, any way you want, right? So my delta distance, if I knew my distance and my velocity, I can figure out my time. So the question is, how long did it take to go 5 meters? So if my velocity is 5 meters a second, the question is, how do I determine how long it took to go 15 meters? Let's do that. So if I said, all right, my delta distance over velocity equals delta time. And I want to know, look, how long does it take to go 15 meters from where I started? So 15 minus 0 meters over my velocity, which is 5 meters per second, equals my delta time. Well, that's just like saying 15 meters, because minus 0 is 15 meters, times 1 second over 5 meters, right? And my meters cancel, giving me what? 3 what? 3 seconds.
Wait, that's 1 second on the bottom, not 15, right?
Yeah, it's 1 second. Because because my velocity is 5 meters a second. It's really 5 meters per 1 second.
Okay, I just want to make
Yep.
sure.
No, you're good. I just want to make sure we're clear on that, right? So I may write this, but I want to start really writing it more like 5 meters over 1 second, so we can do this inverse portion, right? So we can start to do our unit analysis work. All right. Last thing. Okay. Can I go to the next one? Last thing. And this is going to be distance and time. What does this mean? Negative slope, which means I have a what? Negative velocity, right? So so if I go back to here, I'm going to excuse my mess for 1 second. What does this mean? What does this mean about my traveling dude? He's going right. He's not traveling this way. He's actually traveling this way. So he's actually going around. He's actually going in this direction. Because what's happening to my distance? My distance is going from, let's say it's 10 meters, boom, 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 boom. Now it's 5 and 4 and 3 as time moves forward. Does that make sense? And if I look at the slope, right? Again, I look at the slope. My delta distance is, let's say it's 10 meters minus 4 meters. Or excuse me, I'm sorry, take that back. What's my final, let's say here's 4 meters and here is 8 meters, okay? And let's say this is 5 seconds, and 3 seconds. Okay? What's my change in distance? What's my delta distance? How do I do that? Delta distance finals minus distance initial, right? What's my final distance? What's my Yeah, my final distance as time goes on, my final distance is 4 meters. Minus my initial distance, which is what? Wait. 8 meters. And my final time is what? 5 seconds minus 3 seconds. So it's a negative 4 meters per 2 seconds. Negative 2 meters per second. Is that clear? Crystal? Paulina, smile. Okay. Pardon me. Okay. God, 45 minutes. I gotta stop this.